Okay, hi Ani.
Hi Janakiraman.
Okay, so we had established last time that we needed to time quantize and also amplitude quantize in order to take anything into a digital computer, right? So let's just maybe proceed on that line again, right? So we said you have a signal x of t, which is a continuous time signal, and we said you have to time quantize.
Yes.
Okay, and then we said you have to amplitude quantize, right?
Yes.
Okay, and what we said was here you got x of n ts, right? Every ts seconds, right? The sampling period, you would sample the signal and you would get a value which is a real number, and then that has to be amplitude quantized and you would get xq of nts.
Yes.
Right. So this I think we have established well now. So why don't we look at a basic implementation of both these blocks?
Sure.
Okay.
Sounds good.
So let's maybe look at x of t, right? So this is going to be some time signal, okay, like this, x of t, about some bias, you're going to have something like this.
Yes.
Right? Or maybe why don't I just take a sine wave, just to keep it sort of simple, okay, instead of an arbitrary signal. What if I just take a sine wave like this now?
Okay.
And now what I want to do is, I want to do this time quantize, okay, and then amplitude quantize, step by step. So,
Sure.
How do you think we should proceed with this?
Okay. So first of all, I know that I want to get some certain points on the sine wave.
On the sine wave,
So
right?
first step, maybe I should just mark out how many.
Yeah, exactly.
points
Let's
I want.
say this is my sampling time,
Okay.
Ts.
Yes.
Okay. So the gap between any two consecutive vertical lines is going to be Ts. Okay. This is good. Yeah.
Yes.
Okay. This is Ts. Okay. Great.
Okay. And then, so what I want is the set of voltages corresponding to where those lines meet the sinusoidal curve.
Correct.
I need those values.
So you need these
Correct.
dots actually,
Yes.
right?
Correct. Shall we assume that x of t is a voltage?
X of t is a voltage.
Is a
right?
voltage.
So we are going to assume this is in volts.
Yes.
Okay. Yeah, absolutely. So I need all these
Voltages. So it's almost like if I wanted to, I'm looking at it the reverse way.
Okay.
I want to recreate these things. What I would need are, so let us say I have 10 TSS in one period.
Okay.
I would need 10 DC voltages, fixed voltages.
Fixed voltages.
And I would try to kind of, shuffle between those voltages to recreate the discrete time sinusoid.
Right, exactly.
Right.
So now the question is, in a practical sense, is it possible for us to even generate like a voltage at a given time?
At a given time? No, it's not.
It's
right.
not.
So we cannot do that.
We cannot do that, right? Correct. So what do you think is the best sort of an alternative to that?
So what I need to do is somehow at exactly these instants, I need to connect this voltage to some point,
okay,
and disconnect it from that node at other points.
So in some sense, is it okay if we generate a voltage like this?
Absolutely. I think that sounds fair, because in between those 2 points, we don't mind what the voltage is.
Exactly, right?
Yes.
So this is what I'm saying we should be doing.
Yes.
Okay. Okay.
Yes.
So this red curve sort of gives us a practical approximation, right? So in some sense we are saying we take this red dot here, but in TS, we are assuming that that signal is not changing fast enough,
Yes.
right? And this is something we discussed last time. If you have a very fast wiggle there, it means you're not sampling fast enough.
Correct.
You're losing information. So it's safe to assume that in this sampling instant, the voltage does not change. So
Correct.
it doesn't matter where you sample in that instant, and you just hold that data for
That's
that
right.
period.
In fact, we talked about this because we said we should be sampling such that between adjacent samples, the signal should not be changing much
Exactly.
at all,
Exactly.
right? Then you will approximate
Yes.
the signal. So x of nts will be as close as possible to x of t.
X of t, right? Yeah. So in some sense, we are now going to see how we can create this red version
Yes.
of the x of t. The red signal is an approximation to x of t, but it is close enough,
Yes.
right? Assuming that the sampling rate is fast enough, right?
Yes, yes.
So just, what could we call this signal, red signal, right? We are sampling
Yes.
and then holding.
We are holding it for
Right.
some time.
Exactly. So can we just call it a sample and hold?
Yes. So the circuit that builds this will be called waveform will be called a sample and hold circuit.
Yes.
Perfect.
Okay. So this is what we are going to now look to build. Okay. So I can abbreviate that by SH, sample and hold, right? X of t, and what you're going to get out of this is x of n ts, right? So
Yes.
what we want to do now is to just sample that value and just hold it for some time.
Yes.
Now, where have we seen this earlier? What component do you think can do this for us?
See, what I know is that I want to hold a voltage,
Yeah.
and I know definitely that the one component I know that holds a voltage is a capacitor,
Is a capacitor.
right? I charge it to some voltage and let go of it,
Yes.
it will hold that voltage.
Exactly.
Right? Because an inductor will try to conduct current,
Yes.
a resistor will try to conduct current.
Yes.
So a capacitor is best.
Is
to
the
do
best,
this.
right? Exactly. In fact, we had discussed this when we discussed the low pass filter.
Yes, that is
If you
correct.
apply a unit step function,
Yes.
right? So just to sort of revisit what we did earlier, okay? If you apply a unit step function like this, then the input, assuming that it charges instantly like this, the output would simply follow it asymptotically,
Yes.
right? So if you give it enough time, and enough is based on RC,
Yes,
right? The time
yes.
constant RC. If you give it enough time, it will simply charge to that final value, right? So what you can probably do is view this, sample and hold as each one is a different DC voltage, like a step function, and there is enough sampling time, right? It's slow enough.
Right,
Okay.
right.
So that's what we are going to do here now. So as you said, the right thing to do is to simply put a capacitor.
Yes.
But here, can I have a resistor? Can I feed this x of t to this circuit?
No, it won't, because the capacitor will try to follow, because
Exactly.
the resistor will keep charging the capacitor
Exactly.
as the input moves.
Exactly, right? So in some sense, the resistor is not going to do this job for us, right?
Yes.
There has to be some sort of a circuit that connects and disconnects.
That's right, because we know that the capacitor charge stays constant only when it is not connected to anything else that is going to draw current.
Exactly.
Right.
Right? So yeah. So what do you think we can replace this?
So you said you want to connect the voltage and don't connect the voltage.
Yes.
So there are two states.
Yes.
So can we try something, when we need to use electrical equipment, we turn it on and
Yeah.
we turn it off.
Yes.
Right? We call that a switch.
A switch.
Right?
Right?
Maybe we can use that here.
Yes. I think that's a good idea. So we'll represent a switch by this.
Okay.
Okay. And if it is closed, it means there is a short circuit and the input voltage, okay, this x of t, which we said was a voltage there, will get connected to the capacitor.
Yes.
And if you disconnect it, right, then this is going to get disconnected and the capacitor is simply going to hold that value.
Hold the charge.
Okay.
Okay.
So what do you think the the characteristics of a good switch should be.
So it seems like this switch has two states.
Yeah.
Right. So we will need to, so we can see for the resistor, capacitor and inductor,
Yeah.
I remember drawing the equations as well as the voltage characteristics.
Yes.
Right. Maybe we can first write out what the switch does in
Yes.
two cases.
Yes.
Maybe even try to plot the VI characteristics.
Yeah, sure.
For the inductor and capacitor, because they were differentially related, we could not plot the static characteristic.
Correct.
But maybe we can do that for the switch.
For the switch.
We'll take a look.
So so it has two states, like you said, on state and off state.
Yes.
So in the on state, what do you think should happen?
See, you said that the input step happens instantaneously. The voltage has changed instantaneously.
Yes.
And I think here, if you go back to the previous page,
Yes.
I noticed that at Ts, you need to get the new voltage across the capacitor.
Correct.
You have actually shown it rising up directly, immediately.
Yes.
So the resistance needs to be 0.
Yes,
Right?
absolutely. So here R should be equal to 0.
Yes.
Okay.
Which means the two voltages on either side of the switch when it is on are exactly equal.
Are exactly equal for any current.
For any current. Oh, okay.
For any
So
current.
any current. Perfect.
For all I.
Yes.
Right. And what about the off state?
Okay. So on the off state, again I go back to that
Yes.
characteristic that you had shown.
Yeah.
You have shown the voltage as being flat.
Yes.
So the capacitor should be completely disconnected. No current is drawn.
Disconnected. Yes.
So it should be infinite resistance.
R equal to infinity for
Any voltage across it
any
now.
voltage.
Perfect.
For
Because
all voltage
I don't know what
across.
x of t is changing to.
Yes.
But the capacitor should be constant.
Yes, exactly. But of course, x of t is not going to change drastically.
Yes.
That we already know.
Yes.
Okay. So great. So okay. So you also mentioned we should plot the VI characteristics of the switch, right?
Yes.
So what do you think it should be? V versus I. Okay. We are talking of a switch like this. Okay. V is basically the voltage across here,
Yes.
and I is the current that goes through this.
Okay.
So in the on state, okay, let's assume that the switch has been turned on.
Okay.
You're saying that the voltage should be 0
For any current.
for any current. So
Interesting. So
So-
that will just be the x-axis then.
that will just be the x-axis. Absolutely. Right? And actually this is bidirectional, right? In
Yes,
some
it
sense.
will occupy,
Yeah.
negative and positive.
So it just
Right.
goes like this. This is the VI characteristics of the switch in the on state. And in the off state, we said it should be infinity.
That's right.
For any voltage, you should have 0.
Correct. Which means it will be the y-axis.
It will be the y-axis, right? So
And it
if-
can be both positive or negative.
exactly again, right? So this is
Oh, this is an interesting component.
exactly. Okay, so this is the on state, and this is the off.
So now I have a question for you.
Yes.
What decides whether it is on or off?
So what decides? Right. So this. So if you look at the mechanical switch that we have, right?
Yes.
You actually go press.
Correct.
You apply a mechanical force. The switch changes, and internally, if you look at that switch, there is a metal contact.
Contact or no contact,
No,
right? It's
no
physically.
contact, right?
Yes.
Exactly. Though electronically, I think you can also control this with a voltage and stuff like that.
Okay.
But a switch is effectively that. You do something. With some energy, you can turn it on. With some energy, you can turn it off.
So
okay?
maybe what we'll show a third terminal. Will we need to show a third terminal to decide when it's on or off?
Yes.
Okay.
Maybe we can say that there is a control terminal.
There is a control
right?
terminal,
So
maybe.
this arrow, right? Shall I just call it control?
Sure.
Right?
Sure.
And I'll
Yes,
call
that's
it,
best.
Yeah. Okay. Control terminal.
That arrow represents the control terminal.
Yeah.
Great.
Okay.
Great.
Okay. Great. So now what we have therefore said.
I have one more question
Yes.
before we move ahead.
Yes.
Can you go back to the previous page?
Yes.
I noticed something interesting. You said when it's on, the resistance is 0.
Yeah.
When it's off, the resistance is infinity.
Yes.
For any voltage.
Yeah.
What power is dissipated by the switch in on and off states?
Yes. That again is a good question.
In this case, for the ideal switch, the way we have written it, it
Yes.
seems like for any current, if the resistance is 0,
Yes.
the power is I squared R.
I squared R
For a
is therefore
resistor,
0.
this is 0.
Yes.
Oh, this is interesting. And when it's off, there is R is infinity, current is 0.
Yes.
So I square R is again 0, but V squared by R would be a better.
Yes, V squared, because there is a finite voltage.
Yes.
V squared by R is again 0.
Is again 0. So it is an ideal component that doesn't dissipate any power.
Any power.
Oh, amazing.
Right?
Okay.
Yeah. So yes, I think that's a very sort of involved point. I think we'll come back to that a little later. So great. So what we have now is we take our x of t, apply it to this switch and simply connect it to a capacitor, right, x of t, okay. So this is a capacitor with value C, right. Now how do you choose, how do you think you can choose the value of C? Should it be like farads, microfarads, femtofarads?
So in this specific case, I think if you are using an ideal switch, it does not matter.
Yes, it does not matter.
It does not matter.
I think in reality, this assumption that we made, right, will probably, you know, you'll have maybe what, milli-ohms of resistance?
Possible, yeah.
Possible?
Correct.
Something, right? And this might be
In
mega-ohms.
mega-ohms or something,
Right?
So separated by maybe 6 decades.
Exactly.
6 or even more actually, 9 decades.
Yeah, exactly.
9 decades.
9 orders of magnitude.
9 orders
right?
of magnitude.
So that's a good approximation of a real switch.
Yes.
Okay. And you have, therefore, you know, in the on state, I could redraw this circuit in the following way. Some small resistance.
Maybe some small resistance.
Yeah.
Right.
R on. Right. This is C. Okay. And my x of t.
Yes.
Right. Now R on is in milliohm. Now can you tell me what is the best way that I can choose? What should be the choice?
Now I can go back to the previous page where you had shown this charging.
Yes.
RC charging.
Yes.
For a step.
Exactly.
Now what happens is when you throw on the switch,
Yeah.
I need to charge to a new voltage.
Yeah.
It will charge, it will settle exponentially.
Yes. RC ln 2 was the you know, the time constant of that circuit, and therefore if R on into C is sort of much less than the sampling period, right. So you can just say very loosely R on into C must be much less than the sampling period. Okay. So what it means is you connect the switch and then it immediately charges, right, and you can then take off the switch.
You can then take off the switch.
You can then take off the switch maybe after a couple of maybe what, 10 R on into C or something like that.
Yes.
Some estimate, right?
Yes.
So turn off after 10 R on into C, something like that, right? And if the signal is not going to change, right, it has sampled, you know, some value. For example, in this case, it has sampled some value in this region, right?
Right.
And it is going to hold that value now, right? So that's exactly what's going to happen. So if you look at that control terminal, okay, maybe what we can do is we can just plot that voltage, okay. So this is control terminal. This is what decides if the switch is on or off,
yes,
right. So we are going to sample at Ts, okay, and we are assuming that R into C is much smaller. So the control circuit will look something like this.
Yes.
Does this make sense?
Yes.
Okay, some for every sampling period. So this is Ts, 2 Ts, 3 Ts, and it is on for some period, right? I will call this T on.
Yes.
Okay. So every Ts, you are turning it on for a short while, you have sampled that value, right? And therefore, if you simply look at the signal out here, okay, you are going to get x of n.
Yes.
Ts.
The voltage across the capacitor would be x of n Ts.
X of n Ts as approximated by this red curve. So it's going to be like a staircase, small staircase, and as you said, yeah, the staircase may not be ideal, it might be slightly, you know, we looked at this in the low pass filter thing also, right? It's, if the time scale is long enough, then it's effectively still an abrupt jump.
Yes.
Okay. So yeah, so I think with this, we have been able to generate a voltage, right, on that capacitor, right, and that's of course a real number.
Yes.
Right. This is what we discussed last time.